we are going to be looking at naming different aromatic compounds. And instead of naming them with the parent benzene, if they have these common groups attached to them, we can include them as part of the parent. And that's what this section is about, is figuring out which parent you can use, right, and using that as the parent. And when you do that, by definition, the carbon where the group that's part of the parent is will be carbon number 1. You'll see that. And then when they talk about this ortho, meta, or para, that's only done for compounds where there's 2 substituents, where you could classify them as ortho, meta, and para. But you can always use the numbering system. So I'll primarily use the numbering system, and when it's possible to do the other, I'll mention that you could have also named it meta, ortho, or para. Okay, so let's go in here with the examples. Hopefully you've kind of looked at these. This is the sort of example where you need to do some, quote, memorizing, right? You need to just be able to recognize those compounds and know the parent name associated with them. So maybe some flashcards or something is advised to sort of quickly get that into your brain. Okay, and start here. So in this case, this is one of our parents, and it doesn't have any other substituents. So we could just name this phenol. We just want to recognize that is phenol. Of course, it also could be named hydroxybenzene, but the idea is not to name these the parent benzene, but instead to name it as one of the other aromatic compounds. Okay, so in this case, we would want to do some numbering. And again, you always start with whatever group is going to be part of your parent. That's always at carbon number 1. So I'll circle the parent numbers in there. So then this becomes 2-ethyl phenol. Or because there's 2 substituents here, right, it's also possible to call this ortho ethyl phenol. So it's just basically means the relative position is 1. And this is sometimes just shortened to just an O. Well, okay, but I prefer the numbers, right? Just because you can always do numbers regardless if there's 2 or more substitutions. It's sort of a more broad-based meaning. Okay, from here, we're still doing a phenol as the parent. Okay, and now we have the possibility of having bromine at carbon number 2 and then fluorine at carbon number 6, or the opposite. Fluorine could be at carbon number 2 and bromine could be at carbon number 6. And when you have a case like that where the numbering is equal both ways, like 2,6 or 2,6, then you use the alphabetical order as your tiebreaker. So B comes before F alphabetically. So then this would become 1, 2. We get the lowered number as well. And so then this becomes 2 bromo, 6 fluoro, and then the word parent phenol. Okay, and because there's more than 2, we cannot use ortho, meta, or para. So over here, the parent is different. Now instead of phenol, it's anisole. I don't know why he always puts the group at the top, but that's not always going to be the case. It's possible that this methoxy group could have come down here. Still be anisole. I think the only example he has of that is this very last one. But at any time, the parent doesn't have to be the group at the top. Okay, so from here, they're going to be para or 1,4. And so I like the numbering better. So 4 nitro. I want to recognize this is a nitro group. 4 nitro anisole. Okay, stop me if I'm going too fast. So over here, we're going to recognize the parent is benzoic acid as the parent. So then this becomes 1, 2, 3, lowest number possible, or the isopropyl group. So 3 isopropyl, and then the parent benzoic acid. No spacing, right? But benzoic and then acid is technically a separate word. So there's 2 words there. There's no dash, no spacing, nothing like that there. Okay, so from this one, you might recognize that this is toluene. And so we can name it with that as the parent. So in that case, this is carbon number 1. And then the next, I want to go this way so that I can get my next substituent at carbon number 2. Substituents at carbons 2 and 5. Okay. We still need to alphabetical order these. So ethyl and isopropyl. The I counts in isopropyl, but E is still before I. So 2 ethyl, 5 isopropyl, and then the parent, which is toluene. We're still looking at toluene, the parent over here, and look, he put substituents in the same positions. Okay, so still the numbering is 1, 2, 3, 5. But in this case, right, B comes before F in the alphabet. So even though this has a higher number, it still comes first when we put the name. 5, bromo, 2, fluoro, 2. Follow. Edited. I want to make sure that know that there's no break. Okay, so for this one, our parent is styrene, and that's going to be carbon number 1. So then this becomes 3 and 4, the lowest numbers possible. We have N for nitro and I for iodo. Iodo comes first. 4 iodo, 3 nitro. So a lot of people, once they get used to the nomenclature, they like these. Sometimes easier than synthesis. Very systematic. Okay, the parent here is acetophenone. And by definition, this is carbon number 1. I want to go this direction, so I get substituents of 2 and 3 as well. We have chloro, C for chloro, E for ethyl. Chloro comes first. So 3, 6 dichloro, 2 ethyl, and then acetophenone. Parent here is aniline. So we have 1, 2, 5, 2, 5, 2,5 diethyl, parent, aniline. So half the battle is just remembering the name of the parent. This one, parent is benzaldehyde. So we have bromo and then ethyl substituents. So 3 bromo, 2, 6 diethyl, benzaldehyde. And then this one is the only one where he didn't put the group that's being included in the parent in this sort of top position. But it, like I said, it doesn't have to be. It could be any. So we're going to start here. 1, 3, 4. He comes first. This is 3. 4 ethyl. Benzoic acid. Parent. Before we move on from nomenclature, is everybody okay with this? Good. We will move on to aromaticity. Okay, so for aromaticity, there's lots going on. Kind of see lots of examples next time. But one of the things that's a requirement for something to be aromatic is that it has to have a p orbital all the way around the ring and the molecule has to be planar such that those p orbitals will all overlap. For example, you could have a p orbital at every single atom all the way around the ring, but if the molecule is not flat, those p orbitals might not overlap. So we say that the planar structure, series of overlapping p orbitals over the entire ring, is a ring that is fully conjugated. Basically means that there's overlapping p orbitals around the entire ring, no matter how big. And so one way to think about that is there's going to be a lot of resonance as well associated with aromatic compounds, because resonance essentially is the overlap or the delocalization of electrons in p orbitals. Because there's p orbitals everywhere and we're delocalizing electrons in those p orbitals. So this is kind of that first step. But what I want you to really recognize is that in order for this to be aromatic, which it is, then there must be a p orbital all the way around the ring. So you might know that pi bonds are overlapping p orbitals. Unhybridized p orbitals, when they do that side-to-side overlap, they form a pi bond. If you don't remember that, go review what's the difference between a sigma bond and a pi bond. And what you'll see is a pi bond is overlapping p orbitals. And they're not always drawn overlapping, but sometimes then people will draw these lines. So if these are in the same plane and they're right next to one another, there will be an overlapped region. And that is the pi bond. So whenever you see a pi bond, there's definitely a p orbital at each of these carbons. And there's 2 electrons in that pi bond. Whenever you see a carbocation, there is also a p orbital at that carbon. Because remember, a carbocation is really sp2 in its hybridization. So it's using its 3 sp2 hybridized orbitals to make bonds, sigma bonds. And then it has an empty p orbital. That's why it doesn't have an octet, so it only has 6 electrons around it. It's very electron deficient, so we call it a good electrophile. Okay? And the key thing to remember here is there is an empty, right, p orbital. It's hard to draw because in reality it'd be coming out of the plane completely 90 degrees orthogonal, which are in the plane. But there's a p orbital here and it doesn't have any electrons in it. The key is not the fact that it has or doesn't have electrons, the fact that at this carbon there is a p orbital. That's what I'm trying to kind of drive home. So that means there is a p orbital at every single atom in the ring. That's crucial. In order to call something aromatic or even anti-aromatic, right, which we'll kind of talk about next time, there has to be a p orbital at every single atom in the ring. And they all have to be coplanar or to enable full conjugation of those p orbitals, full overlap with the entire p orbital system. And then after that, it has to have the correct number of electrons in order to become aromatic. And you might have learned from the video that the correct number of electrons is Huckel's number of electrons. But it's also potentially easier not to worry so much about those numbers, but to think about the number of electron pairs. So you can either say it's got a Huckel number of electrons, or it's got an odd number of electron pairs. So for example, this has 1 electron pair from the pi bond and no electron pair from carbocation, because remember there's no electrons in that p orbital. So it has a total of 2 electrons, which is a Huckel number. You could memorize the Huckel numbers. Or you could just say 1 is an odd number of electron pairs. So if I have a series of overlapping p orbitals of the entire ring and an odd number of electron pairs, then it will be aromatic. And again, we're going to really focus on what is and isn't aromatic in the next activity. So today is really just about all of the following are aromatic, right? And we're just going to be drawing resonance to show that we can delocalize the lone pair or the positive charge all the way, so the lone pair and a negative charge or a positive charge all the way around. So one way to help with figuring out if you've gotten it to every position in the ring is to number the positions in the ring. So it's really small, I know, but basically I numbered 1 to 5. And if I consistently draw that, just exactly as it looks here, right, with the numbering, then I'll have figured out if I've gotten to all the different positions. So that I'm going to draw it a little bit bigger. So I just kind of want it to look almost identical to exactly how that looks, so that I don't mess up my number. And so that means I'm going to do, so resonance contributor number 1 has the lone pair negative charge on carbon number 1. But now I'm going to start moving it around. And so I can go clockwise or counterclockwise, it doesn't really matter. I'll go counterclockwise just to show that's fine. And I'm going to move the lone pair now to carbon number 4. Because I'm going counterclockwise, but I counted my numbering clockwise, wonderful. But it doesn't matter. Okay, so when that happens, there's a pi bond here, a lone pair here, and there's a pi bond there. And then I just keep going. If I started counterclockwise, it's best to just keep going counterclockwise. Now move that lone pair negative charge to carbon 2. I'm going to draw a resonance arrow, double hooks here. Try to draw the same way it looks. And then you can move your here. You don't have to do numbering, it's just a good way to know you're done. Or you could also think, however many atoms are in the ring, that's how many resonance contributors I need. But I have to have the lone pair at every single atom, and there's 5 atoms in the ring. All carbons in this case, I need to have 5 resonance. So that would be another way without counting. So now I'm just going to keep going, move that lone pair to carbon number 5. So far I've had the lone pair on 1, 4, 2, and 5. So the last one I need to hit is carbon number 5. Going, I will get there. Big. My best. that's the idea, is to delocalize the charge. Sometimes there's a lone pair, sometimes there isn't, to every position. And this is essentially the same thing as we just drew. The difference is the lone pair is on a nitrogen atom. That really doesn't matter at all. Nitrogen versus carbon, as long as it's a lone pair, you treat it like a lone pair. So I'm just going to start moving. In this case, I'm going to go clockwise to show you how to go. So the only thing you have to pay attention to is there's going to be a difference in formal charge. You have nitrogen versus carbon. That's something to do. Okay, so we're going to need a double bond here. One here. Hydrogen, positive charge on nitrogen now. Pay attention to that formal charge. It's a little bit different. But basically, we've moved it from the nitrogen to the number, right? 1, 2, 3. It's carbon 2 now, right? It's up to you how you want to do your number. Okay, so we're going to going clockwise. So we're doing the allylic lone pair pattern. We've gotten here and keep going. So again, 5 atoms in the ring, 5 resonance contributors. That's how you know if you've drawn them all or not. And then one. So that shall have moved the lone pair to every position in the ring. Again, sometimes counting is helpful. Don't see that very easily. Okay, really very quiet today. Either this is easier than normal or just okay. This one, now we have sort of a ring that contains 2 rings, but it's the same process. Again, numbering is helpful, right? But we can also just think, okay, how many atoms in the ring, right? This one, there's 6, 7, 8, 9, so a total of 9. So we're going to need 9 resonance contributors. So it'll take a little bit for us to do this. Again, you can kind of work your way clockwise or go counterclockwise. Right? This does not matter. Okay, so maybe I'm going to go. There's just something about clockwise that's satisfying. Feels more correct. It doesn't matter. Move this here. Going. I'm trying to fit 9 resonance contributors. Here, here. Sometimes when instructors make these, I just wonder why they can't think about giving a little bit more space. This one, going. think I'll just utilize so now we're kind of headed back towards all the positions we missed. We're going moving the charge and locate every other atom. Yeah, we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. We've got 2 more. Okay, so if we think about where kind of, if I numbered this one, for example, first one, maybe number starting from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I sort of went from 1 to 3 to 5 to 7 to 9, back to 2, 4, 6, 8. So it's like hitting all the odd numbers and then the even numbers. So I went from having a carbon number 1 to number 3, number 5. Notice how it goes every other. Carbon number 7, 9, 2, 4, 6, and 8. We can hit every single one when there's a series of overlapping. Space here. 2, 1. This one's got a lot of lone pairs. So by the way, we've been moving around this lone pair, right? In all 3 of these cases. So if I ask you, where is the lone pair? What type of orbital is that lone pair in? I have a chat button open. Nobody. But I wonder if any, there's only 4 students here today, but if any of you guys want to take a guess as what orbital is that lone pair in? P, sp, sp2, sp3.
In the p orbital, right?
Yes, right. So if we can delocalize that lone pair, it's in a p orbital because the electrons are delocalizing in p orbitals. That's what resonance is. Delocalization of electrons in overlapping p orbitals. So I want everyone to recognize that that lone pair that we started with in those last 3 examples, those are all in the p orbital. So what does that mean, for example, for this carbon? What's the hybridization on that carbon? Very well. This one here, the carbon that has a lone pair and an anion. Is it sp2 or sp3? Anybody? You can be wrong. It's okay to be wrong. What do you think? sp2 or sp2?
We make it sp2.
Okay, that's correct, right? So remember that a carbon has 2s and 3 2p orbitals. So if it hybridizes, if it has an unhybridized p orbital left over, which is that lone pair, there's a lone pair in a p orbital, by definition, it can't have hybridized all of its p orbitals. It wouldn't have any left. You know it has one left. So that makes it sp2 with an unhybridized p orbital. Okay, so it might look like this has a steric number of 4 with 3 atoms attached, 2 carbons and hydrogen not shown, and a lone pair. But remember, this lone pair doesn't count towards the steric number. Delocalized electrons don't count towards the steric number. They don't go into a hybridized orbital. They don't count towards hybridization. They go into a unhybridized orbital. So yes, the carbon, this nitrogen, and the other carbon down here, those are all of those are sp2 with a lone pair. Okay, so I mention all of that because we need to talk about that. Because now we're dealing with a lot of lone pairs, right? I've got 3 different lone pairs. So what's going into a p orbital and what isn't? They're not all going into a p orbital. So we know we have p orbitals here and here for the pi bond. Right? This nitrogen is making a pi bond. The p orbitals right there are for the pi bond. Remember that an atom can't have 2 orbitals in the same place. So if there's a p orbital already here for the pi bond, this lone pair is not also in the p. They would be going in the same direction in order to overlap and have that. So as a result, this lone pair is in an sp2 hybridized orbital. The reason why is because this atom already has a p orbital for the pi bond. So that means that the lone pair will go into a hybridized orbital. This means it is not a delocalized lone pair. You're not going to draw any resonance contributors. It's nothing. It doesn't exist for the purpose of resonance. In order to be participating in resonance, it needs to be a lone pair in a p orbital. It's not in it. Okay, so then what's going on with these two? What sort of orbital are they in? Well, in order for this compound to be aromatic, remember I said the criteria, number 1, is there must be a series of fully conjugated p orbitals at every atom in the ring. Which means one of these, and I don't care which one you pick, will go into a p orbital, and one will go into a hybridized orbital in this case. You have to say sp2, because of course, in order for an atom to have p orbital, it can't be sp2. So one lone pair on the sulfur is in a hybridized orbital, not involved in resonance. The other lone pair is in a p orbital, delocalized with all the other p orbitals. Right? This lone pair will only go into a p orbital if that would make it aromatic. If it would make it anti-aromatic, it will choose to go into a hybridized orbital. That's what makes it more stable. Right? So, but in this case, if I put it into a p orbital, then how many electron pairs do I have? 1 pair for that pi bond, 1 pair for that pi bond, and 1 pair in the p orbital. That would be 3 electron pairs. Right? Checks are electron pairs. We have 3 of those electron pairs in the p orbital system, overlapping p orbital system, called up a pi system. This is an aromatic number of electrons, right? 3 is an odd number of electron pairs. This means it's an aromatic number of electrons. So yes, absolutely, one of the lone pairs will go into a p orbital because then that'll make a p orbital all the way around the ring, a p orbital system all the way around the ring. and it'll have an aromatic number of electrons, which will make it stable. So think about what's going to happen on the sulfur. Both of those lone pairs go into hybridized orbitals. There's no aromaticity, right? I'm sure Dr. Gwynn talked about those molecular orbitals. We won't have a filled set of bonding molecular orbitals. They'll be stable and aromatic. So that's not good, right? But if instead of going to sp3 hybridization, it goes to sp2 and puts one of its lone pairs into a p orbital, then it has a fully conjugated ring, aromatic number of electrons, which means a full set of bonding molecular orbitals, which will make it really, really stable. So this sulfur is not sp3, instead it is sp2. What does it give up by being sp2 and not sp3? There's not as good bond angles. In sp3, all the bond angles would be around 109 degrees, right? But in sp2, you have 120 for 3 of them, but the lone pair is there. That bond angle is 90 degrees. So it's like 120 and 90 degrees. 90 degrees for an electron pair is not as good as 109. So typically, increased hybridization makes it more stable, but not in this case. In this case, we'll give up a little bit in terms of bond angle and steric crowding in order to get a full filled set of bonding molecular orbitals, super stable experiments. Okay, so when we are drawing resonance here, we really don't care about lone pairs that are in hybridized orbitals. We only deal with lone pair in the orbital. That's the only one that we care about. Kind of sketch this in. Of course, you'll still draw them, but we don't really care about them. We are going to start at that lone pair in a p orbital, though. So with this one, we picked. We'll just kind of clockwise, clockwise, and then we just kind of keep drawing them by shifting where the pi bond and sure then to potentially drawing any formal charge. Sulfur is kind of like oxygen. So just keep moving one of these lone pairs, doesn't matter which one, in that pattern that we've been doing. And there's 5 atoms in the ring, so there will be 5 resonance contributors. Here. Feels different with what are called heteroatoms, non-carbon based atoms. Really the same thing. Double check. You always should have the same net formal charge on all structures. Here, our last. That was a lot. We're going to continue to talk about aromaticity and p orbitals and hybridized orbitals the next lecture. Okay, so next one is the helium cation. You get to get really good at making your 7-number ring. You're going to have to draw it. There's 7 atoms in a ring. You have 7 resonance contributors. So in this case, we have the positive charge and not a lone pair. So we have to draw the resonance differently. Right now we do.
Question about the above one.
Yep.
I'm confused why the sulfur, like in the last one, or why it continues to have like a positive charge.
It's kind of like oxygen. It makes 3 bonds and has a lone pair. It's positively charged because it's right below oxygen on the periodic table. So basically, like here, it's only making 2 bonds with 2 lone pairs. So the way to calculate formal charge is we take the number of valence electrons, subtract the number of assigned electrons. So like oxygen, sulfur is in the same column, so it has 6 valence electrons. Subtract the number of assigned electrons. So 1, 2, 3, 4, 5, 6. But over here, there would be 6 minus 1, 2, 3, 4, 5. 6 minus 5.
I got it. Cool. I forgot about the
Yeah.
formal calculation. Thanks.
What was that? Yeah, so it's the +1 in the formal charge. Okay. So we're going to be doing the allylic cation pattern. So in this case, we don't start on a lone pair. Instead, we start on the pi bond and shift it over. There's only 1 arrow needed for this pattern. Again, it helps if you do some numbering. You know I need to generate 7. Faster if I don't have to. I just literally just keep shifting it over and just kind of keep going in the same direction. Choose clockwise, you go clockwise. Just counterclockwise. Shifting. Or go. The idea behind this is just recognizing that this is a super stable carbocation. It is, not only is this compound aromatic, but the positive charge is delocalized over 7 different carbon atoms. So there's very much positive charge on any given carbon. Super delocalized. And again, you can kind of do the arrow inside the ring, outside the ring. This sort of thing doesn't matter. So if we counted, let's say we had started numbering starting here at where the carbocation originally was. It's easy to do it that way. It's going to go from carbon 1 to carbon 3 to carbon 5, carbon 7, back to carbon 2, 4, and 6. We'll hit all of them. So the idea is that regardless if it's a lone pair or an empty p orbital, so it's sort of like a filled p orbital or an empty p orbital, right? Like here we have the empty p orbital, the lone pair here we have the filled. Regardless if it has electrons or not, right? That the electrons in the system are delocalized over the entire ring, which makes it very, very stable. That one is so stable that it has okay, so we're going to be doing some review. We'll just start with the synthesis, going from an alkene to an alkyl chloride, radical. And then we did an elimination. Whenever you do an elimination, ask yourself that Zaitsev or Hoffman, essentially, and that looks like Zaitsev. Two hydroxyl groups getting added, both going syn, what we call syn dihydroxylation. That osmium tetroxide. Again, sometimes you see other things like co-oxidants added, like NMO or peroxide, or the workup step here. But just osmium tetroxide. And then we're going to do an oxidation, where the tertiary alcohol will not oxidize. The secondary alcohol will. So for that, you could use PCC, or you could use sodium dichromate.
Quick question for the
Yes.
syn of the hydroxyls. You couldn't use MCPBA or H3O because that would add it anti, right?
Right.
Okay. So OSO4 adds its syn.
Mm-hmm. Correct.
Okay.
You could also use potassium permanganate at its syn, but most people don't, because the problem with potassium permanganate is you have to do the reaction really cold, because it's a strong oxidizing agent and it will potentially oxidize your alcohol even further. Which in this case they wanted to do anyway, so probably would have been okay. But typically, if you just want to do the syn dihydroxylation, potassium permanganate, while much cheaper, very common oxidizing agent, much cheaper than an osmium-based reagent. It has a problem with over-oxidation, which is hard to control, but the colder you do it, the less likely it is to. So sometimes you might see KMNO4. Cold. I'll say something like cold. This is okay. So TMS protection. So trimethyl silyl chloride and some sort of base or triethyl. And then looks like we want to remove the TMS and then add in this extra. I think that's the critical part, right? Getting ready for this Grignard reaction, add in a carbon. So, right, they're just adding in a methyl, so we use methyl magnesium bromide. And then we just do H3O plus workup. That will likely take away the TMS.
Do you have to also write, was it TBAF, or I forgot what moves the TMSCL?
Yeah, so if it wasn't enough to add the acid to remove this, then you could do a third TBAF step. And that would for sure. But basically, TBAF or acid is supposed to remove the TMS. So if you added enough acid, it's likely that the TMS will gone without the need. So sometimes it's written as a separate step for TBAF, and sometimes kind of a case-by-case scenario, whether or not it gets removed and then you don't have to use TBAF, or it doesn't get removed and then you do have to use TBAF. An organic chemist would be able to know whether or not it got removed from analyzing the product and figure out if they need to. Okay, so this is a little bit unfortunate because we haven't covered NMR yet this semester. I know you guys covered it last semester. You're probably somewhat familiar with it. We're going to be doing a big review of NMR eventually in the lab section of the semester. It's going to be group activities. First, we're going to do like more of an introductory activity and then more of an advanced activities. Lots of NMR later. But I'm going to go over it just in case you can follow it. If not, don't worry about it because you're going to be reviewing NMR heavily later in the semester. So I'm not planning on putting any NMR problems on your quizzes until after we've done those NMR activities. But just because it's here, I am going to go ahead and maybe remember a lot of it. So we have he doesn't give us a molecular formula, which is a bit unfortunate. Usually, like with NMR problems, I'll give the molecular formula. It's C3H60 or something. But he just gives a mass. That is only really good to kind of double check your answer at the end. It doesn't really give us any right off the get-go. So we're kind of flying blind without a molecular formula, and that's okay. So first thing we're going to look at is the integration here. I noticed this integration of 0.5. We cannot have integration of 5 because we have to have at least 1/3. We have to adjust these. This is really going to be 1. And in order for that to be 1, I have to multiply all of the numbers by 2. This signal will really be 3 hydrogens, 6, multiplying by 2, and 2, and 2. Okay, so the integration is really 2 to 2 to 1 to 3 to 6. Again, the computer just gives us a relative integration. It doesn't tell us exactly what the numbers are. The user has to adjust that. Okay, so one of the things that I saw immediately is the fact that I've got signal sort of in between 3 and 4. That usually means proximity to an electronegative atom, and most common oxygen. So over here we might have an oxygen, and then we've got these signals that integrate for 2, right? So we would have CH2. So they're both attached to the oxygen, that's why both signals are around 3.5. And then we look and see, okay, what are they, how many neighbors? Right? And we can tell that from the multiplicity. So on one side, there is a doublet. And a doublet means there's only one neighbor. So on one side, there's only one neighbor. So then on the other side, I have a quartet. So that means that it has 3 neighbors. So this is sort of the signal. So if I have this isolated ethyl group, so CH2CH, this is an ethyl group, and I should see this signal as well. So this is a signal that should integrate for 3, CH3, and it has 2 neighbors, so it should be. So more upfield, I should have a signal that integrates for 3, that's a triplet. I have that. So really, this one is that card. That kind of leaves me with. So this is the one that integrates for 1, which means it matches. And it's quite a bit, there's quite a bit of splitting, and we can't necessarily see exactly what the splitting pattern is because it's not blown up, and sometimes there's tiny ones on the edges that you can't see. But if I take a look at this one, I've got 6 hydrogens that are a doublet. The only way to get 6 equivalent hydrogens is to have 2 methyl groups. So if I put a methyl group here and a methyl group here, and they were equivalent, they are, then it would integrate total of 6 hydrogens, and it has 1 neighbor, so we would expect a doublet. So that's kind of here. So essentially, we came up with ethyl oxygen. oxygen. CH2, CH2 methyls. This ether. And if we kind of double check with the carbon NMR. So anytime you have, you can sort of break this up into 0 to 50 and 50 and beyond. These would be any carbon attached to an oxygen. We get really those, we expect 2 of those because we do have 2 carbons attached. And then I would expect to have 1 signal for this methyl, 1 for this carbon, and then 1 combined for these 2. So I would only expect 3 signals over here. It's just carbon attached. So that is the correct structure. And then if you double check with the mass, right, remember we can do that quick calculation. We've got this guy is our structure. So there's 1, 2, 3, 4, 5, 6 carbons. Right? So carbon is 12, 2 plus an oxygen, 16, 8 plus 1, 2, 3, 4, 5, 6, 7, 8. So that's 30, 102. Matches the mass. The last one here. Now they did give the molecular formula. That's helpful. We can do something with that before we even look at the NMR. We can calculate what's called the hydrogen deficiency index, also known as the units of unsaturation. There's an equation for this. Hydrogen deficiency index equals 1/2, 2 times the number of carbon plus 2 minus the number of hydrogen minus the number of halogens and plus the number of nitrogen. X equals halogen. So notice that oxygen is not in the formula. Carbon, hydrogen, halogens, and nitrogen are in the formula. So basically, doesn't matter how many oxygens there are, it's not going to change the value. Okay, so we don't put it in. So for this particular formula, right, we would get 1/2, 2 times the number of carbons, there's 5 carbons, 10 plus 2, minus the number of hydrogens, minus 10. Right? I don't have any halogens, I don't have any nitrogen, oxygens don't matter. That, so 1/2 of 2. So I get 1. What does this mean? This means 1 double bond or much more common to have a double bond than a ring. Most likely to be a double bond. Now it could be a carbon-carbon double bond, but even more common is a carbonyl. When you have 1 double bond and you have oxygens, and you really want to think about, could this be a carbonyl? That would be my 1 double bond, and it would take into account an oxygen. So the mass spectrum shows me a signal sort of to the left of 150. And that means that I have a carbon. I definitely have it. So that's good to know, right? That I need to incorporate that in my structures. Okay, so now I can just look at fragments and think about what's going on. I've got my carbonyl. I have that. I kind of like singlets because they're simple, neighbors, right? So, oh, I have to deal with the integration values first. They just gave me these numbers here. They didn't tell me what the integration is. So to figure out what the integration is, divide by the smallest number, 33.2. So this would be 1 to 1.5 to 1 to 1, which is not good. They need to be whole numbers. So then I just multiply everything by 2, and I get 2 to 3 to 2. This is likely 2 hydrogens. That's good to know. So now I know I have this singlet that integrates for 3 hydrogens. So when it's 3 hydrogens, I'm thinking methyl. Okay. And I'm going to put it directly attached to the carbonyl because it's at an integration, or sorry, a chemical shift 2. Okay. Directly next to a carbonyl will give you a shift of 2. So I don't think there'd be other oxygens in between. If it was attached to an oxygen, it would have been over here. So I sort of got this part of the molecule done. Now I need to work on the other, attached to the other side. So we have 2 hydrogens, 2 hydrogens, hydrogens. It's very likely just a simple CH2, but I forgot the oxygen. Oh, okay. Getting ahead of myself. I'm trying to put all this stuff in. But look at where this shift is. It's at 4. Right? So E means my oxygens. That I can get a shift of 4. So basically this is going to be a CH2. It's a triplet, so it has 2 neighbors. So I will put it next to another CH2. Right? And it has a high shift of 4, so it's definitely going to be next to an oxygen. The other CH2 is not as down, it's more upfield because it's not as close to an oxygen. It's more split because it has more neighbors. So it's got a total of 5 neighbors. That neighbors on both sides, which means it should be a sextet. If you kind of look closely at the and then the last one is this methyl. It should have 2 neighbors, so it should be a triplet, and it's not going to be downfield because it's not anywhere near function negative. Okay, so the sort of we came up with this propyl, then oxygen, then a carbonyl, methyl. That way. And that would match everything. It matches the formula, it matches the NMR, carbon NMR. We've got this carbonyl carbon all the way over here, 170. We've got something between 50 and 100 for the carbon attached to oxygen. This one's carbon way down. Way. And then basically we have 3 carbon-carbon, right? They're not attached to oxygen, they're attached to other carbon. Expected to be 0. So don't worry if you were kind of lost on the NMR. If you really understood it, that's great. You're going to be ahead of the game. If not, don't worry, there'll be lots of video on this later. So, how did that go? Any questions?
I have kind of I'm not sure how to ask this question. I have, I guess, a general question on the aromaticity
Okay.
problems. I understand it for the most part, but I struggle with differentiating between non-aromatic and anti-aromatic sometimes.
Mm-hmm.
So
especially with lone pairs, right, on heteroatoms?
Yeah, so where I run into confusion is when there are 6-membered rings
Mm-hmm.
and they have atoms that aren't carbons, and there are lone pairs on those atoms. So
Right.
I
Okay,
guess,
let's go over an example.
okay.
We'll go over a few examples. And again, this is more of like a question next time. That's okay. Okay, so we have, if we look at, for example, I don't have to have, I'm not going to use oxygen. We'll go over more examples. But let's say, even without an oxygen, we're looking at these two. And let's say that there's some, we don't know, right? Where's this lone pair? What type of orbital is it going to be? So we kind of do this analysis. We go, there's p orbitals, here, 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 here. It's possible that this lone pair is either going to be in a p orbital or it's going to be in sp3. And we don't know which one. We have to figure that out. So if it goes into a hybridized orbital, this would be non-aromatic. There would be no p orbital here. So let's just imagine for a second that it might go into a p orbital. If that's the case, we count up the electrons. So electron pair, 1 electron pair, 2 electron pairs, 3 electron pairs. Assuming it's in a p orbital, we can count it towards the electrons in the pi system. So this would be, right, 3 or an odd number of electrons, which is good because that's an aromatic number of electrons, right? So that means yes, it will definitely go into a p orbital, because when it does that, then that means that there's a fully conjugated set of p orbitals all the way around the ring, right? And there's the right number of electrons for it to be very stable. If we kind of contrast that over here and go, okay, do the same sort of analysis. There's p orbitals here all the way around, and we don't know, right? Is this going to go p or sort of question? And let's imagine, like we did in the last one, that it goes into a p orbital. If it goes into a p orbital, then I've got now 4 electron pairs, which is now an even number of electrons. That's bad. That means it's going to be unstable because those electrons are going to go not into a bonding molecular orbital. They're going to be unpaired, right, in either non-bonding or anti-bonding molecules. They're going to destabilize the molecule, right? So then it just won't do that. Instead, it will go into a hybridized orbital. If it goes into a hybridized orbital, that means we don't have a p orbital at that carbon. We don't have a p orbital at that carbon. It can't be aromatic or anti-aromatic, and it becomes non-aromatic. So it's much more stable for it to be non-aromatic versus anti-aromatic, right? So it will be non-aromatic. Aromatic. So basically, when you have a lone pair, you can think of it as maybe it goes into a p orbital, maybe it goes into a hybridized orbital. If it goes in, it will only go into a p orbital if it would make the right number of electrons for it to be aromatic. An odd number of electrons. If it would make an even number of electron pairs, it will not go into a p orbital. Because if it did and it overlapped with the other ones, it would be anti-aromatic, which is extremely unstable. So instead, it's going to say, forget it, I'm not going to go into it. I'll go into a hybridized orbital. And overall, the molecule is much more stable that way. And then we can't call it aromatic or anti-aromatic because there's no p orbital here. So we've got That's the sort of the difference, right? So it sometimes goes into a p orbital and sometimes. It will only go into a p orbital if it makes it aromatic. Does that make sense, Amelia?
I think so. So
Okay,
when we're analyzing, I do understand having like localized and delocalized. So if we ever have a compound and we find, and we assign localization and delocalization, and then we look at the number of pairs and it's an even number, then at that point, do you know then that it has to be non-aromatic? Like, will that always be the case?
If there's a lone pair that can go into a hybridized orbital, that will make it non-aromatic.
Okay.
I'll give you some examples of cases where it truly is anti-aromatic and we don't have a choice.
Okay.
So
yeah, I'm trying to recognize the pattern, but I'm obviously missing something.
This is the classic example here of the anti-aromatic compound. Because think about the orbitals, right? It's got a p orbital all the way around the ring. And it has a p orbital here. And it has no choice, right? It has an empty p orbital. If it had a lone pair, that lone pair could go into a few different orbitals. But there's no lone pair. It's deficient of electrons. And as a result, there has to be a p orbital that is electron deficient at that carbon. So by definition, we have a p orbital all the way around the ring. So at this point, we are going to be writing aromatic or anti-aromatic. We have no choice, right? Because we're meeting criteria number 1. Now, I like to insert some wording to be really clear. So on my problems, instead of just saying classify this as aromatic, anti-aromatic, or non-aromatic, I will include some words like assuming coplanarity of adjacent p orbitals. It's like, seems like a, but really it's not. Basically what it's saying is if you have a p orbital, you assume they're coplanar, meaning that the molecule is planar. It has not adopted a different conformation. Because if it can adopt a different conformation to avoid being anti-aromatic, it will do so. In which case, we'll never call anything anti-aromatic. Like, majority of molecules are never truly anti-aromatic because they can just avoid being planar, avoid overlapping the p orbitals, and therefore they're not anything. They're just not aromatic, right? So if they can adopt a different conformation to avoid being planar, they're not anti-aromatic anymore. Because if those p orbitals don't overlap, they don't form those molecular orbitals, right?
Right. Okay.
The electrons in them. So if those molecular orbitals don't exist, we don't put electrons in. Okay, so we have this terminology basically that says we assume it can't adopt a different conformation. And that's just for me because I want students to be able to choose anti-aromatic if that's what I want them to choose. And otherwise you would never pick anti-aromatic and it'd be a lot easier. Anti-aromatic or it isn't. So here we go. We've got a p orbital all the way around. We have 2 electron pairs, which is an even number of electrons pairs. So this is anti-aromatic. So in this case, there is no choice because there's no lone pair that we can make a choice with, essentially. So coming over to like an example like this, right? We've got a p orbital here, and then what would it take to potentially get this to be aromatic? Right? I need a p orbital with oxygens, which means I've got to take one of these lone pairs and place it into a p orbital. That's a possibility. If I don't, then it's just going to be non-aromatic. But let's think about whether or not placing it into a p orbital would make it aromatic, in which case it will do that. So if I place them in lone pairs in p orbitals, so that such that I have a p orbital all the way around me. Now I've got 1, 2, 1 electron pair, another electron pair, 3 electron pairs, 4 electron pairs in those p orbitals. So now I have an even number of electrons. So that's not good. That means if I was to place these in p orbitals, it would be anti-aromatic. Now I have a choice, whereas I didn't have a choice before, now I do. Instead of going into a p orbital, the lone pair can go into a hybridized orbital. Now, there's no p orbital at those oxygens, and it's non-aromatic. The other thing to pay attention to is like with the nitrogen. Nitrogen, when it's making, it already has a pyrron, right? Then obviously this lone pair cannot go into a p orbital because the p orbital is from the pyrron. So it can't have two things in p orbitals in the same direction. So we know we don't do anything. So, but here's the confusing thing. Even in a case like this, kind of drawn all over it. 7-membered ring here. If I don't think about the electron pairs, and I just think, well, can I draw resonance here? Just start moving my electrons around. Dr. Gilly showed me. I can draw a lot of resonance contributors that are all useless. They're wrong. Why are they wrong? They're wrong because this lone pair is not in a p orbital. If it is not in a p orbital, it is not overlapping with the p orbital next door, and there's no resonance. It might look like there's resonance, but there is no resonance. It's all about the orbital. What orbital is that lone pair in? Not in the p orbital. There's no resonance. So you might think I can draw this and I haven't violated any rules, but you kind of did because you're involving a lone pair that's not in the right orbital. Right? And resonance is just delocalization of electrons in overlapping p orbitals. Okay. Hopefully that makes sense. Try to digest that a little bit. And,
Okay.
and then come back tomorrow with more examples. Go over these again if you.
And we're going to do more practice with that tomorrow, right?
Oh yeah, we're doing lots of practice with that. And I think there's like 2 or 3 that I have a different answer than Dr. Finn. So don't be surprised if you get them all correct according to his key. But a lot of the different, some of it comes into, there's like 1 or 2 that he's just like wrong. And then I like to use this wording, which can sometimes get a different answer.
I noticed that with the worksheet too. There were exceptions, quote unquote, but it was kind of like wondering with the coplanarity.
Yeah.
If
I
don't know how we would be expected to know what
that's
shape
exactly
the molecule
why
could adopt.
That's exactly why we just make this assumption. That's not
Okay.
really true because unless there's some sort of conformational rigidity associated with it, typically you can adopt a different conformation, in which case it will really be non-aromatic. But it's hard to know, like, is this one going to adopt a different conformation or not? How do I know, right? So that's why we just kind of make this assumption. That way it does kind of make it easier to assign. For example, like one of the answers that's different might be cyclooctatetraene. I don't know what he has for it. But according to my wording here. Assuming coplanarity of adjacent q orbitals, you know there's a q orbital all the way around the ring. There's pi bonds all the way around. So if we assume those are coplanar and we count up the number of electron pairs, it's an even number of electron pairs. So we have to call this anti-aromatic, according to the assumption that the p orbitals are all going to be planar. The molecule itself will be planar. Of course, the book talks about how cyclooctatetraene is not really planar, right? I'm not going to be able to draw a nice picture of this for you. It's like a tub shape or something. It didn't come out too bad. But it exists in a non-planar conformation in order to avoid being anti-aromatic. So truthfully, it's non-aromatic. And if you don't make this assumption, then you're going to say it's not aromatic. But then you have to know that it can be non-planar. And that's kind of hard to know. How would you know as a student? So for me, I would just say, making this assumption, we're going to call it anti-aromatic. So that might be where they, change the answer from what he has. I've just been teaching this a long time, and I know it's easier if I do.
I still don't understand that the one with the two oxygens, how that's non-aromatic.
So I thought about temporarily putting the lone pairs into p orbitals, each one into a p orbital. If I did that, I would have a p orbital all the way around. But when I counted up the electrons, I saw that I had 4 electron pairs. 1, 2, 3, 4. I am not counting these because those are in hybridized orbitals. So I count 1, 2, because I said this was in a p orbital. I can count it 3 and 4 if I make this one. You only count electrons in p orbitals. And if I do that, I have an even number of electron pairs. That's going to make it anti-aromatic. That's not good. That's not stable. So as a result, these won't go into p orbitals. If they don't go into p orbitals, then they go into a hybridized orbital, then I don't have a p orbital of these oxygens. I don't have a p orbital, I can't be aromatic or anti-aromatic. Because if you look back at the criteria for aromaticity and anti-aromaticity, it talks about it in there. You have to have a p orbital all the way around the ring for it to be aromatic. Same thing with anti-aromatic. So if it's not true that there's a p orbital there, then it will be non-aromatic. Basically, it's only going to go into a p orbital if it makes it aromatic, meaning you have the odd number of electrons. If it would make it anti-aromatic, it's not going to happen. Let's look at one more example here. Let's look at a 5-membered ring. 3 lone pairs. So which lone pairs are we going to count? Only those that are in p orbitals. So I've got a p orbital here, here, and here. I have a p orbital on the nitrogen that's part of the pi bond, which means this one is in a hybridized orbital. It doesn't count towards the electron count. So in order for this to potentially be aromatic, I need a p orbital on this oxygen because I need one all the way around. So it's possible one of these lone pairs goes into a p orbital. The other one goes into a hybridized orbital. If one of them goes into a p orbital, I would have a p orbital all the way around. Then I count up the electrons. I've got an electron pair here. I've got an electron pair here. And I can count this electron pair because it's in a p orbital. Now I have 3. This is now an odd number of electron pairs. 3 is an odd number. So because it's an odd number of electron pairs, then it's going to make it aromatic. If it's going to make it aromatic, yes, absolutely, it will go into a p orbital. orbital. It makes it aromatic. And I have the right number, the odd number. So this will go into the orbital because counting it makes it aromatic, makes the third odd number of electrons. When I went and said, okay, I might put these in p orbitals, but then I counted it up and I went, oh no, that's going to be 4 electron pairs. Oh, scratch that. Those aren't going into p orbitals. They only go into p orbitals if it gives odd number of electron pairs in those p orbitals. If it was to give an even number of electron pairs cumulatively in the p orbitals, then it's not going to happen. Then you just say, okay, those go in hybridized orbitals and they don't count. In which case, there's no p orbitals there, it's just non-aromatic. I know that's a lot of logic to follow, right? But I think if you watch this video back a few times and see the examples, you're gonna pick up on it. And then try to do the activity from next time and we'll go over it.
Dr. Gilly,
Yes.
I'm a bit confused with the hybridization. I think you said earlier something about sp2 having the p orbital.
Okay.
Does sp3 doesn't, right? Like I'm thinking about like that energy diagram.
Yeah, no, that's good. That's good. We should go back to the energy diagram because this part often kills students and it's something they learned a long time ago and then forgot about. Let's go back to the energy diagram, for example, for carbon atom. You've got the 1s electrons, 2s electrons, and then there's the 3 equal energy 2p. So how many electrons are in a carbon atom? So you look on the periodic table to figure that out. The other way to think of it is we know there's 4 valence electrons. Valence does not include the core electrons. So 1s, sometimes it's even left out. 4 electrons, we don't care. These are we call them the core electrons or the non-valence electrons, right? How do we know these are valence? These ones are not valence, right? We know that because this is the highest n number. N equals 2 versus n equals 1. Whatever the highest n number is. So we don't really care about the core electrons. Those are just going to stay in their 1s orbital all the time, no matter what. So over here, right, we can say, how can we hybridize these? We can, if I was to hybridize to sp2, what would that look like, right? I would be hybridizing my 2s and 2 of my 2p's to get to sp2. That's where the sp2, which means I have a remaining unhybridized p orbital or 2p orbital. I usually say 2. Okay, and then let's imagine it's a carbon atom. We want to talk about the lone pair, right? We're going to look at this carbon atom. Because that's an anion, I'm going to go ahead and add an extra electron. I have 4 here that I can put into these orbitals. And I have an extra one because of the anion. So 1, 2, 3, 4, 5. How that can work out. I know that looks weird because it's like, why is this one higher energy? Lower energy. But remember, right? It looks like it's higher in energy, but is it? No, because it's not stuck in this p orbital. It's delocalized with other p orbitals, right? So this is really a delocalized lone pair, not a localized lone pair. So it's actually much more stable up here because it's delocalized than it would be down here. So this is what this looks like. So it's got 3 unpaired electrons in sp2. Those are making the sigma bonds. Right? It's got the sigma bond to this carbon, and this hydrogen. It's got 3 sigma bonds, which it's making with these hybridized orbitals. and then it has a lone pair in a p orbital that's overlapping with the other p orbitals. So when I say it's not possible for the atom to be sp3 and have an unhybridized p orbital, it's because if I took this and I, instead of making it sp2, I made it sp3, I would have to hybridize that last p orbital to get there. And if I wanted to get to sp3, I would be hybridizing all of these. That means I have no remaining unhybridized p orbital. So it's quite possible my electrons, 5 electrons, could go 1, 2, 3, 4, 5. Now this is my lone pair, right? So we have two possibilities for that carbon. It could be like this, or it could be like this. If the lone pair is in a hybridized orbital, it's not delocalized, right? If it is up here in a p orbital, it's delocalized. But it will only do that not only if it can be delocalized, but if it's part of a ring, it has to be also aromatic. So if it's not part of a ring, it will do it for any sort of resonance delocalization. But if the ring is the extra kind of kicker, right? It's like, yes, this is no longer the 7-membered ring. That's going to be this scenario, right, where the lone pair is in a hybridized orbital. And that's because this is very, very different than something like this without the ring. I can have 7 atoms with no ring, and those electrons will go into a p orbital because it'll have a bunch of resonance and be really stable. The problem with it doing that in this case is, yeah, it has a bunch of resonance, but it doesn't overcome the fact that it's going to be anti-aromatic. Because now that you're in a ring, now the terminal p orbitals overlap to form a ring, and we get those molecular orbitals, and it's not going to be stable in the molecular orbitals. Okay, so it's really kind of confusing, but it's going back to that sp2 and sp3, what that looks like, hybridized orbitals atom.
I guess I'm a little confused because like the ring example on the right there. So you were saying it's non-aromatic. Okay, so it could go into an sp3 or a p. But my question is, how, with being sp3, there's no p orbital. So like, how is that possible?
So
I'm confused.
okay, this is the same sort of carbon as this one, right? And I'm making 3 sigma bonds, and I have a lone pair. The lone pair, if I had hybridized to sp3, my lone pair would be an sp3 hybridized orbital. If I hybridized to sp2 with an unhybridized p orbital, it would go into the unhybridized p orbital. In this particular case, if it was to go into the unhybridized p orbital, right, then it's going to be overlapping with all of these other unhybridized p orbitals. You're going to get anti-aromatic instability. Why is that? Right? What do the molecular orbitals really look like? Did he go over frost circles in the video?
I haven't watched the video. I read the book, and it did go over frost circles.
Okay. So basically, with a frost circle, you're drawing the 7-membered ring, and then you're putting a line through the center, and here's the energy of the bonding molecular orbital. So essentially, with the 7-membered ring, right, what do my molecular orbitals look like? They look like, here's the even point. They look like 3 bonding molecular orbitals and 4 anti-bonding molecular orbitals. How many electrons can I fit in these? These are bonding.
And the bonding 6.
Yes. Okay, so these are anti-bonding. So 6. So 1, 2, 3, 4, 5. Let's go back up here and look at this How many electrons does it have if this is in the p orbital? It has 8.
Yes.
Now, if I come back over here, and I have to add 2 more, where do they go? There.
The anti-bonding.
Yeah, that's
And they're
that.
unpaired.
This is like a diradical.
Yes.
You know radicals are unstable, right?
Yes.
So this is like a double radical. It's totally unstable with 8 electrons, 7-membered ring. In order for the 7-membered ring to be stable, it can only have 6 electrons in the field. If it has, which is by the way, an odd number of electrons.
Yes.
If it has the extra electrons, those destabilize it overall. So what's it going to do? It does not want to form these molecular orbitals with that many electrons.
Oh.
So
Great.
it's just going to go ahead and not form them. How does it not form them? Don't put this in a p orbital, and all of a sudden there's no p orbital here, and I don't make these through overlapping 7 p orbitals.
So they stay in the sp3, right?
They stay in the sp3,
Oh, right.
right?
Yeah.
And then we don't have that bad set of molecular orbitals. It just doesn't exist. It's not going to be stable this way, so it will not do that.
Yes, that makes sense.
Okay. So what is its other option? Right? Its other option is I'll hybridize all 3 of my orbitals, form sp3. I've got my 5 electrons. I'm going to put them in here. I can make 3 sigma bonds. And I'll put my lone pair in a hybridized orbital, and then it won't be in a p orbital, and it won't overlap with anything, and it won't form that.
Yes, that makes a lot of sense.
Okay.
This
Yeah,
time the book it's a lot, you know, it's
It is a
tough.
lot. It is a lot. It
Yeah.
really is a lot. This is a challenging chapter for sure.
So my last, I'm just being paranoid now. So when we just count the steric number and determine the hybridization like normal, if you were to ask us what is, I guess, the hybridization.
You just
for,
remember that you don't count electrons in p orbitals for the
Right.
steric number.
the ones delocalized. So
Yes. So, for example, you would count this lone pair because it's in the sp3 hybridized orbital, so it counts. That means it's sp3.
3. Okay.
But you don't count this one. We decided this was actually going to be in the p orbital because that will make it aromatic.
Yes.
If it's in a p orbital, it doesn't count, so this is only has a steric number of 3 in that carbon sp.
Okay, I don't know why I was so confused that it can't be sp3. I thought it only had to be sp2. But
No,
it
it can be
makes sense.
sp3.
It makes sense though when you showed
Okay.
that and all that. Yeah. Thank you.
You're welcome. All right, I'll see you later.
Bye.
I think you're the only one left, so bye.